Today's class, we're moving on from the work from Tuesday's class, where we looked at the Euler method for solving first order, second order differential equations. The first order, second order differential equations that we examined in last class were the case of a falling body in the presence of a drag force. We looked at the first order differential equation for velocity as a function of time, second order differential equation for the position as a function of time. So we're going to build on that as a foundation for today's class. I want to talk today at the beginning of the class about two types of errors in numerical calculation. One's called approximation error. Another one's called truncation, rounding error. So we'll discuss that over one slide in a couple of examples. I want to point out the problem with the Euler method that we developed in the last class, and a solution to the problem with the Euler method that's called the Runge Kutta methods that we'll develop in this class. And then we'll look at some examples of using Euler and these Runge Kutta methods to solve both first order and second order differential equations. I'm going to use first order, second order differential equations in today's class that have, in one case, exponential solutions, exponential growth or decay. In another case, sinusoidal solutions. So we'll look, which are very common, obviously, in physics. So that's kind of the plan. Actually, here they all are. Before we get going with the computational physics side, these are just the two differential equations that I'm going to work with today. Actually, at the top here is last class's differential equations. The first order one for the velocity of a falling body. The position of a falling body is the second order equation. We work with both of those, but we supplemented those two free fall equations with the drag force to make them more interesting for our numerical calculations. A couple of simple first and second order differential equations for today's class that allow us to illustrate solutions with exponential growth decay, solutions with sinusoidal oscillations. This equation here, this is the rate of change of the charge on a capacitor when you short the capacitor through a resistor by closing this switch. So this is a first order differential equation that has a exponential solution to it. There's many other cases in physics of exponential solutions to physics problems, but we'll look at that case. And then the other one I want to look at is this second order differential equation here. This is the equation for a mass attached to a spring. There's a restoring force if you stretch or compress the spring. It causes oscillations of the mass on the spring. It's represented by this differential equation here. It has solutions that are simple sinusoidal solutions where the mass oscillates with some amplitude, some characteristic frequency, some characteristic phase. And so we'll study that. So here's a little cartoon for it. Okay. So that's going to be the differential equations we're going to solve later on. But I want to start with a comment on these two classes of errors or inaccuracies that occur in numerical calculations. One class is what we call approximation errors. I'll make the distinction about that. The second one is truncation errors. I'll make the distinction about that. The approximation errors in our calculations will come about because we're approximating the solution to the problem, or the function that is the solution to the problem, by using a Taylor approximation for the function, or a Taylor's theory for the function. And specifically what I mean is when we use our knowledge of the function, say the position of the mass on the spring, or the charge on the place of the capacitor. When we use our knowledge of a position and charge to calculate the positional charge at a future instant, a moment in time, when we do that with the Taylor expansion, we're going to do it with the Taylor expansion, keeping only some terms in the Taylor expansion, because there's an infinite series in the Taylor expansion. And what we did in the last class was just keep the first two terms. And we ignored higher order terms. And so that is a approximation. That's what we mean by the approximation error in the context of and numerical solutions with the Euler method. And every time we step forward in time, from the current time to the future time, calculating the current future value of the function from the current value of the function, we're making this approximation error, and step by step by step, we make this approximation error over and over again. And so it could accumulate, it could build up, and that's something to worry about. So that's the approximation error. You can make it smaller by taking smaller steps. You'd have to take more of them, but you can make the approximation error smaller by taking smaller steps, because the difference between the function of the future value of time and the function of the current value of time becomes smaller. And so that's a way of reducing approximation error. And you would make it worse, bigger, if you took bigger steps. You might want to take bigger steps to save the computer time. So if you take bigger steps, the danger is you're making these approximation errors larger. Okay, what about truncation errors? That refers to a distinct type of error. Rounding errors, truncation errors is a different type of error. It's the fact that in the computer, when we're coding with Python, if we have a floating point number, well, we're representing that floating point number in the computer in some little group of bytes in the computer, and we're storing that number with a finite number of digits, so to a finite accuracy. And when we work with that number, do calculations with that number, then because of this rounding, this truncation, there's some uncertainty, inaccuracy, error associated with that, and that's the truncation or rounding error. There's a case where it's especially dangerous, and there's a case that actually often comes up, and that's when you're taking the difference between two large, similar floating point numbers. So if you've got two large similar floating point numbers, the difference between the two large similar floating point numbers is small, and then that blows up, that amplifies the rounding error, the truncation error on that difference of two small large numbers. So whenever that comes up in a calculation, in a computational computer calculation, you want to worry about the inaccuracy, your rounding error, your truncation error when you're doing differences. I was going to show you, I think let me show a couple of examples. Concrete examples of truncation errors and approximations errors. I'll start with the approximation error. So I got two in my directory here for the class. I got two more notebooks, one for approximation errors and one for truncation errors. And I'm just going to show them quickly because they're just illustrations of that last slide. So this is a calculation that we met in I think the first week of classes, which was the calculation of, say, the value of the exponential of a number using the Taylor series. And we also did the value of the cosine of a variable using the Taylor series. And when you do that, you calculate the terms in the Taylor series to some order. So that is you incur an approximation error when you do that. So in this first cell here, I'm going to calculate the exponential of some variable x. And I'm going to calculate, and I'm going to set that variable to 1. I'm going to calculate the exponential of that. And I'm going to calculate it both by my own Taylor series calculation to some order in the Taylor series that I'll specify, and by calling a function in a Python library package to calculate the exponential. So I'll let the computer function calculate it, but I'll also calculate it. My calculation is this little bit of code here. So I've called my value the approximate value for the exponential because I'm going to calculate it with Taylor series, and I'm just going to do it to the certain order. The order is this parameter here. I'm going to take it to 6th order. So I'm going to add up the first 6 terms in the Taylor series, and that's what this little calculation does here. I initialize the quantity I'm going to calculate to 0, and then I add on 1 by 1 with this for loop the terms in the Taylor series. If you remember, it goes as x. That's the first term for the Taylor series and exponential, plus x squared over 2 plus x cubed over 3 factorial. That simple pattern is a nice reminder of what the Taylor expansion looks like. And so that's my calculation here. So I do that calculation, and I set this parameter 6 here. So I'm doing it for the first 6 terms. You notice actually, in this case, I realized I'm not importing numpy as I would normally do here for all my functions like sine and cosine and exponential. I imported another package, math package, that has all those functions in. But numpy, I don't think had factorial in it. So I imported math with factorial because I was going to use it here. Anyway, I compare my calculated value with the math package value of the exponent e to the 1. And here are the 2 values. And you see they're not exactly the same. And this is an example of a approximation error because I only took the first 6 terms. Now put this in the context. So at least I took 6 terms here. In last class, in Euler method, for the falling body, we calculated the value of a function, positional velocity of future time and the current time by only taking the first 2 terms in the Taylor expansion. So by comparison, I'm being much more accurate here, but I clearly have a discernible difference. There's another example down here with cosine, but I just wanted to show you concrete case of one approximation error. Let me also show you that I think the truncation errors, how they play out in Python or in code, are a little bit more interesting. Okay, I got 3 examples there. I just walked through them. They're sort of interesting. First example, right? Actually, all 3 examples are related to the fact that in the computer, it's storing a floating point number with a limited number of digits to store it, so that there's obviously potential inaccuracy, a rounding truncation error. Okay, so as an illustration of this truncation or this rounding error, here I got a really big number, a 1 to the power 20. the one with 20 zeros after it, and I'm going to add 1 to it. And define a new number, C, which is 1 plus 1 to the power 20. So it's 1 with 19 zeros after it, and then a 1. Obviously, those two numbers are different. I mean, they're similar, but they are different. But if I was to ask my Python code to print out, I'll print out A and B, and I'll ask here if A equals C, if these two numbers are the same. We know they're not. But if I ask if they are the same, let's see what we get. This says they are the same. So Python thinks these two numbers are the same. They're very nearly the same, but imagine you were doing differences of large numbers. Then this might become a problem because Python would has zero difference between these two large numbers, but there was a difference between these two large numbers. So that's a truncation error. Okay. So here's a second example of truncation errors. Again, the context behind this is that Python is going to store numbers like in this example, 0.1, 0.2, 0.3 as in a limited number of bits and as bits. So it stores them as bits in certain limited number of bits. I define A and B. A is 0.1 plus 0.2, so obviously 0.3 for a human. B is simply 0.3, so the same as A. And then we're going to ask the same question of Python to, well, it can print out these two numbers. And then does B equal A? So we know B equals A. Does Python think B equals A? And if I run this one, it thinks they're not. Thinks they're not the same. And so it's saying false, where obviously no, we know is true. The problem is because it's stored 0.1 in memory as some number of bits representing 0.1 and 0.2 in memory as bits, some number of bits representing 0.2, and then it's added together the bit versions of 0.1 and bit versions of 0.2. So it's incurred a truncation or rounding error, and the value of A is not exactly 0.3. And so therefore it thinks that A and B are not exactly the same. So that's another truncation error due to the finite number of bits. And then finally, this example here. So I've got a quantity here that X is very small. I've got a quantity Y that's very large by comparison to X. I've added 2x, Y. So I've added to the tiny number, the large number. I've then, after that operation, I've subtracted off the large number. Again, this is something to us. Look, you add on a number, then subtract off a number to the original floating point number, you're going to have the same number. But when the computer is doing this, it's got some limited number of bits that is storing the small number. It's adding on the limited number of bits that represent the big number. It's subtracting that off, that limited number of bits off. Each of those steps is going to incur rounding truncation errors. And so this is another example where to us, obviously, z equals x, because we've added and subtracted the same number to x. But according to our calculation, Python code, that z and x are not the same. And in particular, in this case, right, z and x are substantially different. You know, they're different by 10% here, because we've been adding this big number on and subtracting this big number off. And then truncation errors on the big number and adding it on and subtracting it off are killing the precision of this calculation. So the moral of the story was, you can, in these truncation errors, rounding errors, make big errors, especially when you're looking at differences between two large similar numbers. Okay. So now let's walk back to the problem of numerically solving differential equations. Let's spot the problem with the Euler method in numerically solving differential equations, and let's fix the problem with the Euler method by introducing these higher order, they're called a Runge Kutta, after the two mathematicians that came up with it, methods for solving ordinary differential equations. So this is a picture of the Euler method. This is one step of the Euler method in constructing the value or future value of a function by position from the current value of the position. This is the picture of many steps as you compute the trajectory of the projectile from the original position of the projectile by making many steps here. I have said before, probably got buried, but when you make one step using the Euler method, you're using the Taylor series and approximating the function to just those first two terms in the Taylor series. You're ignoring the higher order terms in the Taylor series, the largest one, which will be in proportion to that square of the time interval for your step. So you're making a single step error that goes as the time interval squared. So there's obviously, if you make it 2 times smaller, then you can make the precision 4 times better. When you consider the whole trajectory, the whole time interval that you're doing the calculation, you make many of these approximation errors. And the problem is, depending on the situation, they can accumulate, they can add on to each other in a sort of coherent way and make a large error. In the case of a finite time interval made of many steps, then the error goes as the time interval error goes as not the square of the time interval, but just as the first power of the time interval. So that means that if you make the time interval shorter, you know, supposing you half it, you'll make the calculation better, but only by a factor of 2, not by a factor of 4. It's better by a factor of 2, not by a factor of 4, because the downside of making the time interval shorter to reduce the error in the single step error is you're going to have to make many more of those steps. So that partly counteracts the advantage you've got from making the time step smaller. And this effect, where you kind of incrementally, step by step, build up, accumulate a sizable error in your numerical calculation, is a big problem for the Euler method. I mean, you can try get around it by making tiny steps, but that's a big cost of computer power. There's a better way of doing it. It particularly comes up, it causes catastrophic problems in the two cases that I'm discussing today. So when you have like exponential growth, that often comes up in solutions to differential equations. Exponential growth, this time step error in Euler method creates a catastrophic problem there where you'll reconstruct the wrong exponential. The exponential growth won't grow as fast as the analytical solution or a more accurate numerical solution. It's catastrophically wrong. You can even get what should be an exponential decay from Euler method. You can get it to oscillate because of this sort of catastrophic error that's occurring because of the very simple Taylor approximation that you're using. You also get catastrophic errors with Euler method if your solutions if you have sinusoidal solutions that just oscillate on through time, you can get effects where like the oscillations grow in size, violating energy, or they decrease in size, violating energy, and the phase changes in a way that's not correct. And so the Euler method becomes untrustworthy because of the very simple approximation you're making at the basic level of what's at the individual level of each step. Okay, so we want to improve the accuracy of the Euler method for solving ordinary differential equations. And here's a suggestion of how we might go about it. Again, this is showing the problem that we're incurring. In red is the true function that we want to solve for. In black is what the Euler method does in figuring that function, computing that function numerically. What it does is take the value at this point on the left, the current time, to calculate the value of this point over here on the right, the future time, takes this value and then adds on a little increment that is determined by the slope of the function at this point on the left. If the slope of the function is getting shallower, then you're going to make an error. And if it was steeper, you're going to make an error. So that's the source of the approximation error, because you're ignoring changes in the slope. We're ignoring the quadratic and higher order terms in the Taylor approximation, which correspond to changes in the slope of the function. So, I mean, the most obvious idea, I think, is that, well, if I'm making an error by just calculating the function at time t plus delta t by just the first two terms here, the value at time t and the slope at time t, why don't I just add in the next term? That seems pretty straightforward. So I would add in this term that involves a second order differential of my function evaluated at time t. I could add in the third term, right? Could add in the term that involves a third order differential of the function at time t, and add that term in, and so on and so forth. We're going to go up even one order higher. We're at the fourth order differential of the function. We could add in that a term for that at time t. That sounds all very good as a way for accounting for the approximation error in the Euler method, is to add in more and more terms in the Taylor expansion approximation that correspond to the higher and higher order differentials, second order, the third order differentials, and so forth. The problem is that when you specify the problem, we're specifying, remember, we specified the problem by turning any ordered differential equation that we met, practice first or second orders, into into one or two first order differential equations. In general, we don't know the second, third, fourth order differentials of the function. What we're working with in the numerical method is knowing the value of the function at time t and knowing the value of its differential at time t. We don't know these higher order differentials. So that's a problem. And what the Runge Kutta methods do is they don't calculate, they're not able to calculate directly what these second, third, fourth order differentials are. Rather, they estimate the second order, third order, fourth order differentials just from the knowing the first order differential and the function's value at different times. So they make estimates of these higher order differentials and their corrections based on what you've specified to your code, which is the first order differential. Okay. So that's what Runge Kutta is an attempt to walk to higher order in the Taylor series, Taylor approximation, to get more accurate steps, calculate the function of the future time more accurately than the function at the current time. Just some words here. The Euler method is what we would call, in this language of Runge Kutta methods, the first order Runge Kutta method. It's accurate to order delta t for its individual steps. It's making an error at level of delta t squared. A better method is the second order Runge Kutta method. This is the first order Runge Kutta method, which goes to order delta t squared in the Taylor series, and therefore makes a error at the delta t cubed level in single steps. So that's an improvement. We'll see how that works. What is very commonly used, right? So that there are out there in scientific libraries, common packages for doing Runge Kutta. Runge Kutta 4 is a very common order that Runge Kutta gets used at. Is some sort of compromise between being more and more accurate the higher order you go into, but more and more complicated the higher order you go to. So somehow Runge Kutta 4 emerged as, I don't know, its preference for how complicated versus how accurate it was wanted. Just like all of these numerical computational things are compromises between accuracy and time. This is another compromise between accuracy and time, complicated time. Okay, so we're going to talk about these two additional methods. We've now recognized that Runge Kutta first order is just the Euler method, just a glorified name for it. But there are two levels of higher order methods that we want to explore. This is the second order Runge Kutta. And I try to make a picture of it. And then I wrote it down, concretely down here. The problem is, again, we want to know the value of the function at time in the future time t plus delta t, from the value of the function of the current time t. That's the problem we want to solve. In Euler method, Runge Kutta first order, we just use the slope evaluated at this time t. In the second order Runge Kutta, we supplement this quantity, the slope at time t of y, so y prime at time t, we supplement it with the slope evaluated at time t plus delta t. So we're going to use, instead of just one time, the time at the beginning of the time step, now we're going to use two times, the time at the beginning and the end of the time step to find the slope. Well, think about it. If we're just using the slope at the beginning, then if the slope changes, we're going to make a mistake, obviously. But now we're using the slope at the beginning and the end of the time step. So we can use that information to see whether the slope has changed and to try and make a correction for it. And the correction is just a simple one, right? It's often written in this way, that the value of the function of time t plus delta t is the value of the function of time t plus this correction that's going to depend on the slopes and the time interval. This correction is now the average of, comes from the average of when you evaluate the slope at the start of the time interval. That's what K1 is. When you evaluate the slope at the end of the time interval, that's what this K2 is. So we're just averaging these two slopes at the beginning and the end of the time interval, instead of just taking the slope at the beginning of the time interval to calculate the future value of the function from the current value of the function. And that's Runge Kutta second order method. Yeah.
Why is there a y dependent in the y?
This, I think I wrote this, yeah, so the reason for that is what you want to evaluate the slope at this point here, right?
But that is just characterized by t plus dt. There's no y dependent data.
So if you think about the general expression for the differential equation, right? Y prime equals, can be some function of the independent variable t and the dependent variable. So it can be a function of y. And so if you step forward and y changes, it could be that you've got to you need that coordinate. I think I think the problem is probably that the examples I've given so far, that's not true. Like the falling body, if the the differential equation is that the rate of change of the velocity is equal to the acceleration of gravity. So you don't have that situation.
Right.
Yeah.
But I guess since y is always dependent on t, so you can still write it as a function t. And that's the only variable t.
Yeah, I think the point is you are literally changing the value if this is going to, if this depends on y. So if this didn't depend on y, the slope, like the slope of the velocity equals acceleration of gravity, then you wouldn't, this will be irrelevant. But so supposing it did depend on y, then you're going to evaluate not at the y that is the value of the current time, but you're going to evaluate the y that is changed based on the slope of the current time. Does that make sense?
Yeah, but maybe we can.
Yeah, maybe if I could come up with a concrete example of it, might become clearer, I think. But I think that strictly you don't want to use, we're not even using y, but in principle, if you were using y, you'd want to use a different y. But the way I think of it more generally is that you are just using these two slopes evaluated at the beginning and the end, and you're using the average to better handle a change in the slope.
Just in terms of like this, is this still like a Taylor expansion, like based on a Taylor expansion, just with like, I guess the object of the expansion being K1 plus K2 over 2 with the delta T factored out? Like, is that like the thing we're expanding around?
Yeah, I think we are trying to do the Taylor expansion, but we don't have a second order differential, right? So we can't literally put in a y double prime term. So how are we trying to calculate the effects of a change in slope, which is a second order differential? We're averaging the slopes at the beginning and end of the time slice.
Oh,
So we're trying to mock up that additional term that goes as delta t squared that has the second order differential without knowing the second order differential. So we're using two slopes to do it.
okay.
So this is second order Runge Kutta. Yes.
May I ask those two real quickly?
Yeah.
Thank you very much.
If we jump to this is, I don't know whether this will make it worse or better. This is Runge Kutta 4. Okay, so this is an attempt to handle not just the rate of change of the slope, the second order differential, but the next two terms in the Taylor expansion, Taylor approximation, which involves the third order and the fourth order differential. We're going to try and handle all those. But remember, we only know the first order differential. We can only calculate the first order differential. So the way it works is it evaluates four first order differentials. It evaluates them at the beginning of the time interval, the end of the time interval, like we did before, but it also evaluates them in the middle of the time interval. And it actually evaluates them at the middle of the time interval for two different values of y. So that's what I'm picturing here. So my little blue lines are four separate evaluations of the slope of the function y at different locations in time and potentially different y values. Yeah.
So does that mean that those middle slopes are being weighted more heavily in the?
Yes.
Oh,
Yes.
sorry, I
Yeah.
didn't see that, yeah.
Yeah. So they get weighted more heavily. This weighting, I can only say this in words because there's algebra behind here to explain this weighting that would overwhelm us. But this particular weighting corresponds to the weighting in the Taylor approximation, the Taylor series. So you've got, like a 1/2, the second order differential, a 1/6, the 1/3 factorial for the third, and so on. Those weightings of the terms in the Taylor series determine these weightings that are in here. So this is mathematically equivalent to those weightings. So maybe you could imagine, now we've gone from two estimates of the slope that try to account for the rate of change of the slope. If we take four estimates of the slope, we can account for the rate of change of the slope, the rate of change of the slope, and the rate of change of the slope. That's the basic idea. And so that's the calculation that goes on here. And this is sort of a Runge Kutta 4. And so this one is meant to correctly handle the Taylor expansion up to the fourth order in delta t, and it's going to make single step errors that are at the scale of the fifth order in the Taylor expansion. So that's the value of this method. Okay, so what we're going to do is we're going to apply our old Euler method, and then in addition, this Runge Kutta second order, this Runge Kutta fourth order to these two examples. I'll work mainly with the first example of differential equations. And this time look more at the accuracies or inaccuracies of the differential equations. I put this slide here, which is really just summarize on the right-hand side the differential equation that we're going to be working with in my code. And just to sort of summarize the code in this sort of pseudo code way of what work we need to do to supplement last class's Euler method, Runge Kutta 1, with these new Runge Kutta 2 and Runge Kutta 4. So that's what we're going to have to do. And if you remember, the key elements of the code from the last class, and they're the same key elements in the code in this class, are we defined two user functions that were connected to one another. And then we went through a loop, walking through discrete space, calling those functions. So there was the user function that described the Taylor series approximation we were making for taking a step from one location in time to the next location in time. That was this function here. And then there was the second user function that described the calculation of the slope of the function that we needed. Remember, we specified the problem in terms of one first order differential equations. That I specified the slope, and so we had a function that calculated the slope. And then, you know, we just went round a loop, calling the Euler function to calculate the new value of the function from the current value of the function, and that calculation involved calling the function that embodied the first order ordinary differential equation. So this is really kind of the way the code works in this picture here. I even put in the fact that where you've got to start with an initial condition is the word. So we're going to do that. We're going to do it with our new ordinary differential equation, first order differential equation. It's this differential equation here that the rate of change of the charge on the place of the capacitor is in proportion to the charge on the place of the capacitor divided by the time constant, the RC time constant. So this is just some fixed parameter. So here is the key differential equation. And so when I go to the code, I've changed the ordinary differential equation from what was like the one for free fall velocity or the free fall position. I just changed this to return the calculation of the slope for this differential equation. So that's the nice thing about the way we laid everything out in the last class, is that we laid it out in a way, if we change the problem from falling bodies to a capacitor, charging or discharging, the only thing I have to change is one little one line code to change the ordinary differential equation for the discharging, charging of the capacitor versus the falling body under gravity. So I'm just going to make this change here. The other thing I got to change though is that, well, we don't only want to use Euler method, we want to use RK2 and RK4. And so I'm going to, I'll switch to my code at this point, but I'm going to, in addition to my user function for the Euler method, I'm going to supplement it with user functions for the RK2 and RK4 methods. So those are going to look a bit more complicated because we had those more complicated expressions involving multiple evaluations of the slope or the differential of the function to calculate the new value, future value of the function from the current value. Okay, I'm gonna go here, no, here. And I got this example. So this is the very first cell of my code where I was in the last class incorporating the functions from library packages that I need, and I defined my own user functions, one for the Euler method and one for the ordinary differential equation. And I just expanded it now. This is exactly the same way of calculating the new value of y from the previous current value of y. I expanded it with a new user function, RK2 I called it, and another new user function, RK4 I called it, that calculate the next value of the function of y next from the current value of the function, the y, the and the time increment based on slopes of the function that are calculated from this, will be calculated from this representation of the ordinary differential equation. So that's what I'm doing in these functions. It took a little bit of typing to get that in there and get not make a typo and get it right, but I got it right in the end, I think. So these are these RK Euler with RK2 and RK4. And I'm just using the formulas that I wrote down, where you can Google or whatever, that are in the class notes. So that's that cell. I mean, you wouldn't want me typing this one, of course. Yeah. Here's the cell. I laid this out in 3 cells. Here's the cell where I actually, set up the parameters I need. I define the discrete time that I need. I initialize parameters that I'm going to need, and then to do the calculation. So the whole work of setting up the specific problem and doing the calculation for the solution of the problem is in this one cell here. The cell above is just general functions that I'm going to use. So I've got my discrete time. I didn't make it very, I made it pretty coarse here. I've got 100 steps with 0.1 second time intervals. So I got 10 seconds worth of time. I'm going to set up some initial values. So the differential equation was that the rate of change of the function is the negative value the current value of the function times some constant, some decay constant that I call lambda. And here I'm just picking I'm just going to pick a couple of values of lambda. Actually, I was playing with this code before class, so I always have to be careful about it. I want to start with, I'm going to start with discharging the capacitor. So the capacitor is going to start, say, charged up. And it's this decay constant is this number here. So I just picked those numbers. So this could be the discharging of the capacitor. Well, if you remember back to class 4 on ecology or population survival, it might be the exponential decay of a population of rabbits in a field due to lack of resources. So it's a solution to many problems that have a exponential decay curve as a solution. Okay, so I'm gonna define some proxies for variables, right? T is my proxy for the time variable. It's just an array of the individual ticks of time in my discrete time. So that's my time proxy. I've done that with linspace to build it. I initialized three other proxies for the solutions that I'm going to calculate for the charge on the capacitor after some time t, or the number of rabbits in the field after some time t, or the radioactivity of a source after some time t, all those things for an exponential decay curve. YE will be my solution from the Euler method, and then Y RK2, RK4 are the solutions from the more sophisticated Runge Kutta methods. I'm going to initialize their first value. We've always, whenever you're going to do a numerical solution, you can only you've got to have a starting point. It's a little different from an analytical solution where you can write down a solution, right, without actually specifying the initial conditions. This is often very useful to give you some picture of how this whole thing works. Here without a starting point, there is no numerical calculation. So I set the initial value of the population of rabbits in the field, of the charge on the capacitor, or the number of radioactive atoms to Y0 for each of these solutions using the three different levels of sophistication for solving the problem. I'm also going to compare to an analytical solution for the exponential decay. So just that I know the analytical solution to a differential equation where the differential equals negative times the function itself times a constant, a constant. I know its solution has this form, an exponential decay. Then I'm going to calculate by looping over discrete time the Euler method solution, the Runge Kutta method solution, and a Runge Kutta second order and fourth order. Look, obviously I could have, it's a little bit silly, I could put them all in this one loop, right? That would have saved some time. Yeah, I think I was cutting and pasting, and I made them three separate loops, but they could all be one loop, and each time I would go through the execute the code in the loop, I would just calculate each solution. Okay, so let's run that. And in that instant, we have calculated our three solutions using the three different methods. And remember, I really didn't do much in terms of the code I had in the last class, turning it into the code in this class. I just had to change that tiny part, one line in the ordinary differential equation specification. Then I did have to add the Runge Kutta 2 and Runge Kutta 4's functions. Okay, so let's take a look at the results. I've got this figure down here where I'm going to plot three things. I'm going to plot points to the Euler method, the Runge Kutta 2 method, and the Runge Kutta 4 method here. And then I'm going to draw a line. I'll draw a line for the analytical solution. So I've got blue for Euler, least accurate in the Taylor expansion. I got green for Runge Kutta 2, intermediate accuracy, and I got magenta for Runge Kutta 4, most accurate in our Taylor expansion. And then I've got the exact, at least a proxy for the exact analytical solution. That's the YA. I don't know. That's not really relevant. So we'll run that. And here are the results. What did we expect? We expected a exponential decay with a decay constant of 1. And that's what this looks like. If the decay constant is 1 in 1 second, I don't know, I think we lose 63% of the number of radioactive atoms or rabbits or charge on the capacitor. And every second after that, we lose another factor of 63%. And so that's what you're seeing here, basically. The red solid line is the analytical solution. On top of the red solid line are actually both Runge Kutta 2 and Runge Kutta 4. We only see the second one that I plotted, Runge Kutta 4, but Runge Kutta 2 is buried underneath it. I can see, look, a little bit of green peeking out there. So those two are kind of falling on top of the red line, at least on this level of accuracy that we can see on this level of plot. They resemble the analytical solution. The blue points are the Euler method, which generally follows the trend, but is not perfectly accurate. We can see the inaccuracies, the systematic inaccuracies on this plot. So we're seeing that as we increase the sophistication of the treatment of the Taylor expansion, we improve the accuracy and the correspondence to the analytical solution. I'll just show you, I want to talk about the plotting. This is just the same time range again, 10 seconds. This axis now, let's ignore that later. It's really the difference between the analytical solution and each of the 3 numerical solutions, Euler, Runge, RK2, RK4. So, they all in the previous plot kind of fell along the analytical solution, not quite so for Euler method. But here I plotted the difference between analytical solution and numerical solution. Now you see the accuracy of RK4 in which are the magenta points, which are all lined up along 0. So at least on this resolution, it agrees with the analytical solution. You see that RK2, the intermediate precisions, sort of lines along the analytical solution pretty closely, but starts to diverge at the end. You see that the Euler method is actually, we consider the past, but sort of catastrophically diverging at the end. So this is this problem that I mentioned that Euler can, and it's particularly a problem with exponential-like solutions or sinusoidal solutions. It can catastrophically start to depart from the truth, here the analytical solutions. And that catastrophic deviation just starts to accumulate and roll on like a snowball as it departs from the analytical solution. And, it might depend whether it's a problem or not a problem, depends on how long into the future you want to project. You want to look a long time in the future, something oscillating or something decay, then you're going to run into trouble with the Euler. Yeah.
RK4 is eventually going to diverge, right? And that would, how long would that take?
Yeah, I think that's a very hard question to answer in general, right? Because this problem depends on, well, was it a polynomial solution, or was it a exponential, or was it sinusoidal solution? So But your question is very important, Mark, because if you're doing a calculation, right, you want to know, did it diverge or not?
Yeah.
So what do you have to explore that? Well, you have the fact you can change the time interval in your calculation and explore how sensitive you are to it. And so I think that that's way, in any real life numerical problem, that's what you would do. You would have to justify your solution by changing the time interval, changing the order of the Runge Kutta, and showing that things are stable. If things are unstable, then you know you have to go to higher order, shorter times. So that's discharging the capacitor, because we discharge the capacitor, or we sadly let the rabbits starve in the field, or we let the radioactive source decay away. You can also see, let me just show you, this is easy to change here. Supposing I made this a negative decay constant. And now we got double negative, because I got the rate of change of y was equal to minus y times the decay constant. But now I've got the decay constant itself is negative. So canceling out two negatives, I got the rate of change of the function is equal to the function times a positive quantity. So that's exponential growth, right? So that's like how the stock market might go up, or how the with unlimited food, how the rabbit population might go up. That's a exponential growth problem. So let's just run the whole thing for that too. So I just made that one change. And here are the exact solution for the exponential growth. Remember, now it's growing by every second, it's going to grow by this, factor of 63%. By, it's going to, so it grows dramatically within 1 second, right? That's over here, it looks like it's not growing at all, but it's just because of the scale. If I made a log plot, you can see that it's growing dramatically at every second here. The analytical solution is the red line. The magentas are on top of the red line, as best as I can tell. They're the most sophisticated calculation we do. We see here that the green points are departing from the magenta points a little bit, so that there is a error in Runge Kutta 4 with these time intervals. We're seeing that the blue points have sort of catastrophic. We got a wrong time constant here. We're getting a wrong time constant for the Euler method because we're making this simple mistake of estimating the value future time from the current time for each step based on the slope at the beginning of the time interval. And that slope is changing. And every step, we're making the same mistake. And every step adds to the mistake we make. And so we get a catastrophically wrong calculation. You'll see that here too. But here it kind of looks a bit like the plot for the decay rather than growth. Well, again, when you pick out the difference between the truth and the numerical solutions, both the growth and the decay have the same sort of fractional inaccuracies or that are incurred. Let me jump to the homework assignment and just say a few words about that. So the homework assignment asks you to make the same sort of calculation as I just did here for the charging, discharging the capacitor. Do the same thing for that other differential equation that I mentioned, which involves oscillations. So that's the mass on the spring. And in the assignment here, it tells you the values of parameters to pick, the discretization of time to pick, and exactly what to plot. I want to say a few words about, you know, how I would go about doing this. Let me go back here. Okay, so this was a solution I put together for the homework problem. But my Euler RK2 and RK4 are exactly the same as the Euler RK2, RK4 from the charging, discharging paths. There's nothing different there. The only difference is the ordinary differential equation that's describing the mass oscillating on the spring. So that's the equation, the user function that you'll need to change because you're not charging or discharging a capacitor, you're having a mass on a spring oscillating. And so you've got to change this function here. Now remember the way that and I think this came up in Tuesday's homework, the way that we're handling second order equations, this general approach is to turn them into a pair of first order equations. This is always the way these numerical solutions, computational solutions to differential equations go. So in that process, you introduce a new variable. It's kind of the velocity of the rate of change of the position. So it's the velocity of the mass on the spring. One of the differential equations is simply that definition of this new variable, that the rate of change of the position is the velocity. So that's one differential equation. And then the second differential equation is the differential equation that was the original second order, but now cast in the form of this new variable. So that second order differential equation was the second order differential for the mass spring system is equal to the mass divided by the spring constant times the position. Now we're going to replace the in that second order differential equation, we're going to replace the second order differential of the position by the differential of the velocity. So that's our second differential equation. That's what these two lines are. This line here is this notation can be confusing, but this is this equation that says the differential of the position equals velocity. Y1 is the velocity. This equation here says that the differential of velocity equals negative k over n times the position. When you're calling this like when you called in homework for Tuesday's class, when you call that we're going to play this trick where we're making the meta variable. I'm not sure that's really the right word. The meta variable, say uppercase Y in my class notes, that contain two elements, two individual arrays. There are two elements. One corresponds to the position and one corresponds to the velocity. So this Y here is an n by 2 array, the two corresponding to position and velocity, the n corresponding to all the times. So all these calls to the Euler RK2 and RK4 look at essentially the same. Except when I'm calling these functions, I'm calling them with this guy here, this y here, this y here, this y here, is the two values of the position and the velocity of mass on the spring at that moment in time, from which you're going to calculate the position and velocity of the spring at the next instant in time. So you're passing two values, position and velocity, to the ordinary differential equation. You're getting back two new values, rather than in the charging, discharging, you're passing one value, getting back one value. So that's the key difference there. But other than those few changes, I think you should be able to just make a few changes to take the first order problem and create a second order problem. I better finish that. Any questions on all that? If you have any, we are starting to get more complicated homework solutions. If you have any questions, you can just email me and I can try and answer. Sometimes I can answer them in email, make an appointment, or go office hours or next office hours will be Monday, or if we wanted to make an appointment ahead of that, that's fine. Okay, I'm done. Thank you.